I hate to spoil the fun time, but I guess we have to start so that we keep on time. Welcome to the second session of the conference. And in this session, we have 3 talks. And the first one will be given by Monica Ghobadi. She just graduated from the University of Toronto, and she's now working at Google as a software engineer. Her thesis was on congestion control in data center. And during her stay at Toronto, also she worked on using TCP to rate limiting YouTube video streamings and sizing buffer in the internet. Monia?
Thanks, Rami, for the introduction. Hi, everyone. I'm going to present TCP pacing in data center networks. This is a joint work with my advisor, Yashar Ginjali, who's sitting over there. So let me first begin by talking some facts about TCP. TCP is a mature protocol that has been extensively studied over a number of years. TCP is a window-based protocol, which means that every TCP source sends a congestion window size of packets at the beginning of each RTT. Most TCP variants focus on the evolution of congestion window size over RTTs and ignore the effect of congestion window size changes in sub-RTT timescales. And this might cause some damages to the router and buffers. Ignoring these sub-RTT timescale, ignoring the burstiness in sub-RTT timescales might cause some damages to routers, which meaning that it might increase the queuing delay, it might cause packet losses and reduce the throughput. TCP pacing is a way to address this problem. In short, what TCP pacing does is that it spaces evenly the congestion window size of packets through the entire round trip time. And by doing that, pacing tries to mitigate the burstiness in every TCP source. There's also an increasing interest in using TCP pacing in data center networks. As the ever-increasing link speed in data centers as the link is increasing in data centers, the challenge of building routers with bandwidth delay product is becoming higher and higher. And so data center providers decide to build routers with smaller buffers. But the small buffer routers and small round trip time in data centers bring the disparity between the total capacity of the network and capacity of individual queues. And this disparity is big enough to make TCP congestion control system inefficient. On the other hand, the bursty behavior of distributed system network traffics compels us to fully understand the effectiveness of reducing burstiness and looking into the tail latency of flows in these networks. In distributed networks or in data centers, the median latency doesn't usually mean much. Say that in a search engine, a search query is distributed among thousands of servers, and the median latency has no bearing in the search results because the server has to wait for the slowest flow to finish. These tail latency increase is usually caused by the short-term unfairness in TCP, and this is an issue that pacing might be able to address. So TCP pacing has a few potential that I want to highlight here. It might provide better link utilization on small switch routers, on small switch buffers. It might provide better short-term fairness among flows of similar RTTs, which potentially can improve the worst flow latency. We might also be able to circumvent the slow start completely, and we might be able to save a few round trip times. Or we may actually use a large initial congestion window size with pacing enabled. So the contributions of this paper is that here we study the effectiveness of TCP pacing in data centers. And we look into we verify that by mitigating bursts in packet transmits, pacing is able to actually reduce the packet drops, but there is a limit to it. We observe that benefits of pacing diminish as we increase the number of concurrent connections beyond a certain threshold, which we call point of inflection. After this point of inflection, as we increase the number of flows further, pacing doesn't have much benefit, and actually it starts to perform worse than non-paced. So our results offer two new insights. First, it may not be appropriate to derive conclusions about effectiveness of pacing by just looking at a fixed network with fixed number of buffers, with fixed buffer size and fixed number of flows. Actually, depending on bandwidth delay product to buffer ratio, benefits of pacing varies. And our results is going to help to explain the seemingly contradictory results in the previous works. In the research community, some papers make a decision and make a conclusion of, oh, pacing is too good, let's pace through the entire lifetime of a flow. And other papers show that, no, pacing is not good, let's just disable it by default. Now, results shows a way of explaining why these papers have contradictory results. Second, we introduce a new term, inner flow burstiness, and we argue that by increasing the number of concurrent flows in the system, there is another phenomena called inner flow burstiness that is causing paced TCP to perform worse than non-paced. We verify our model using testbed experiments, and we verify the correctness of our lower bound on the point of inflection point. So let me just give you an intuition for the inner flow burstiness. Let's consider a network with bottleneck capacity C, maximum buffer size B, and n long-lived flows. And in steady state, on average, every flow is sending W packets in every RTT in a paced or non-paced manner. Previous works that have been studying TCP, they usually make the assumption that number of flows and N and C are large enough so that they're not depending on each other. In this case, in our study, we actually explicitly, we don't want to make that assumption because we want to make W to be, we want to represent W in terms of number of flows. So let's look at a paced flow. Here, I'm showing a perfectly paced flow that the number of packets, the congestion window size, is evenly spaced through the entire RTT of the lifetime of the flow. Now, let's look at an interval called delta. The probability of a packet existing in that time interval delta is a Bernoulli trial with probability W delta divided by RTT. Now, what happens if we increase the total number of flows? If I introduce another flow, there might be a packet in that delta time, or there may not be, with another flow, and so on. So let's define a random variable x as the total number of packets in that interval delta. X is actually a binomial variable with probability p. By increasing the total number of flows, the probability distribution of x increases, and hence the inner flow burstiness in that interval delta increases. So let me just go through the basic intuition of our model, and I leave the details to the paper. Here, let's look at two cases, two systems, the best case of non-paced and the worst case of paced. What I mean is that in the best case of non-paced, we have n flows, and here I'm zooming into one RTT. So I have one RTT and I have n flows. In the best case of non-paced, each flow is sending W packets at equal time intervals with each other. So their bursts are not colliding with each other. This is great for non-paced. On the other hand, the worst case of paced TCP is happening when each flow is sending as a paced manner, but the inner flow burstiness is happening and flows are synchronized so that every flow is sending n bursts at the beginning of each time interval. In the paper, we have details that paced TCP is going to perform better than non-paced TCP as long as n is less than W. And with that, we present a lower bound on the effectiveness of pacing as a number of flows. As long as the number of flows are less than CRTT divided by B, pacing has better performance in terms of throughput and flow completion times. Obviously, this is just the lower bound because here we're just assuming that the best case and worst case. In reality, when there's randomness, this lower bound, the benefits of pacing might diminish after this lower bound. So in order to validate our results, we perform an experimental study in a test bed. Here we have a set of servers and set of clients, where the servers are sending RPC flows to clients. We have a hardware delay emulator that emulates delay by storing packets and then sending them at the appropriate time. We use the flow sizes of 1, 2, 3 megabytes between the server and client. We modify the bottleneck bandwidth to be 1, 2, or 3 gigabits per second. And we use an RTT of between 1 to 100 milliseconds. Then we measure the bottleneck link utilization by reading the statistics from the router, from the ports every 12 seconds, as well as the drop rate. And then we measure the average and tail flow completion times by capturing the TCP dump in every host. And we define the flow completion time as the time that it takes for the first bytes of the packet to be sent until the receipt of the last acknowledgement packet. So first, let's look at the very base case experiment, where I'm going to give two examples when there is no congestion in the network and where there's congestion in the network. And these two examples offer the two basic laws of TCP pacing. In the no congestion case, we limit the bottleneck capacity to 1 gigabits per second, and we use only one concurrent flow between the bottleneck. So, because the access link capacity is also 1 gigabits per second, just one flow is enough, and it's not going to cause any packet drops or any congestion in the network. In the second case, when there's congestion in the network, we actually add a second flow to the network, meaning that now there's going to be congestion because the capacity of the access links add up to 2 gigabits per second, and the bottleneck link is only 1 gigabits per second. So we use these two examples, and then we look at the utilization over the lifetime of the experiment. So on the x-axis, we have time in terms of seconds, and on the y-axis, I'm plotting the bottleneck utilization between paced and non-paced traffic. So in first case, because there was no packet drops, obviously we don't really have to pace. And pacing is because there's no packet drops, pacing is having 38% lower utilization. In the second case, there is actually packet drops in the non-paced case because there's congestion in the network. But by pacing packets, pacing is actually mitigating these bursts of packets in the router buffers, and hence it's actually having a higher utilization. This is actually easier to explain if we look at the flow completion times here on the bottom. So I'm plotting the CDF of flow completion times on the first case when there is no congestion in the network. The dashed line is showing the non-paced case, where the flow completion time of almost all of the flows is almost 1 RTT. The reason is that the flow sizes that I used are 1 megabytes here, and the RTT is 30 seconds. So when the congestion window size becomes fully open, TCP just sends all of the packets in a blast, and then it receives the acknowledgement back in 1 RTT. So almost all of the flows after the congestion window is fully open finish within 1 RTT. On the other hand, in paced case, what happens is that pacing is making actually packets, the last bunch of packets to arrive at the end of the first RTT. So we have to wait another RTT to receive the acknowledgement back, meaning that most of the flows are going to finish within 2 RTTs. But if we look at the same plot, the CDF of flow completion times in the case when there is congestion in the network, we see that pacing is still, they are finishing within 2 RTTs, which is good because there's a little packet drop. But on the non-paced case, they see packet drops and they back off and retransmission, and then they're not able to. The tail latency is actually suffering a lot. So this was the basic case, and everybody agrees on that. Sometimes there's no reason to do pacing because there's no congestion in the network. Why would we pace? But what I want to drive at is that even on the second case, when there's congestion in the network, there's actually a limit to it. So let's look at the case when there's multiple flows in the network. And what I'm going to do is that I'm plotting I'm repeating the same experiments, but now I'm changing the number of flows from 4 to 100. And then I'm comparing the bottleneck utilization between paced and non-paced case. According to our model, the lower bound on the point of inflection is 58 in this case, which I marked by n star here. And as you can see, until before this n star, until before this lower bound, paste is actually able to have higher throughput and similarly lower packet drops and lower average and tail flow completion times. But as soon as after we pass this lower bound, then pacing starts, the benefits start to diminish, and at 80 flows, non-paced is actually performing a little better than paced traffic. So the takeaway is that as the number of concurrent connections increase beyond a certain threshold, the benefits of pacing is diminishing. We repeat the same experiment. Here we are setting the buffer size to be fixed. Now I repeat the same experiment with a different buffer size, and I'm observing the same behavior, meaning that as the number of flows is increasing beyond some threshold, the benefit of pacing is starting to diminish. And this is going to actually help to explain the seemingly contradictory results in previous work. And in a study by Agrawal et al., they decided that we shouldn't paste because they looked at a network with 50 flows, a bandwidth delay product of 1,200 packets, and a buffer size of 312 packets. According to our model, the lower bound on the point of inflection is actually 8 flows in this system. And they were looking at 50 flows. So the chances of them going beyond this point of inflection is higher. And it makes sense to me. On the other hand, there's another study by Kulik et al., and they conclude that we should pace because they looked at a network with only 1 flow, bandwidth delay product of 91 packets, and a buffer size of 10. And according to our model, the lower bound on point of inflection is actually 9 flows. So they were before the lower bound, before the point of inflection. And their results is, well, pacing is good, it's helping, let's pace. So now an interesting question is that I was looking at a fixed buffer size. What happens if I change the buffer size and set the actual number of flows in a network to be this lower bound? What are we going to see? So here what I'm doing is that I'm changing the buffer size, and then I'm looking at, and according to the buffer size, for every buffer size, I'm calculating the lower bound of the point of inflection, and I'm actually setting the total number of flows in the network to be that number. And then I'm comparing the bottleneck linkage utilization. As you can see, pacing is still a little better, but things might go bad, might get worsened as we go beyond that. Similarly, we see a same trend for average flow completion time and tail flow completion times. But for packet drop rate, we always are seeing that pacing has lower packet drop rate. This means that pacing is helping with the packet drops. It is reducing the packet drops by pacing packets. But what I want to emphasize and what I want to drive at in the next few slides is that this inner flow burstiness that I introduced earlier in this talk is actually hurting pacing, and it's causing drop synchronization in these pace flows so that the utilization is dropped. Now, if we want to look at the drop synchronization, let's just Before that, let's intuitively look at the clustering effect. Here I'm plotting 2 matrices with each element ij in this matrix is representing the probability of packets of flow I to be followed by packets of flow j. So in the left-hand side, I'm plotting the non-paced case, where the diagonal of this matrix has the highest probability, meaning that in a non-paced case, it's more probable of packets belonging to the same flow be followed by packets of its own flow, meaning that burst, 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 burst. On the other hand, in the right-hand side, in the paced case, packets of the diagonal of the matrix actually has the lowest probability, meaning that the packets of paced case are actually intermixed with each other. And the probability of packets of flow I be followed by flow j is actually, be followed by flow I again is actually pretty low. So let's look at the drop synchronization and what does it mean in terms of drop synchronization. To measure the drop synchronization, we used the NetFPGA router and we counted the number of flows that are affected by a drop event. We modified the event capturer module in the NetFPGA router, and we instrumented it that every time that there's a drop in the router, in the NetFPGA router, just report the flow IDs of all the flows that have been affected by this. And here I'm plotting the CDF of number of flows that are affected by a drop rate for different flow for different number of flows. So as you can see, if the number of flows is below the point of inflection, pacing still has a little bit higher drop synchronization, but not too much. But look at the case on the far right-hand side, where the number of flows is well above the point of inflection. Here, if you look at the 300 line, which means that when I have 300 flows have been affected by 80% of packet drops. So if you look at the vertical line in the pace case, in the non-dashed case, solid case, 300 flows have been affected in 80% of packet drops, whereas in the non-pace case, this is only 10%. Before wrapping up, I want to talk a little bit about future trends of TCP pacing. This result haven't been published in my paper, but we have experiments that shows that actually by using another level of pacing on top of the per-flow pacing, which is per-host pacing, or to be fair, per-egress port pacing, we might be able to mitigate this inner flow burstiness, and we might be able to achieve actually higher throughput, lower packet drop rate, and better flow completion times. The goal of per-host pacing is to sort of rate limit based on the aggregate rate of each of these flows. So if we have if I know the rate of each of these flows that needs to be paced, then the per-host pacing on the NIC maybe can introduce a gap between flows that are coming out of a host. And I did this with modifying a NetFPGA router with a packet generator, but I haven't published the result yet. So to wrap up, we re-examined the TCP pacing effectiveness, and we demonstrated that when pacing brings benefits in the data center environments, but there is a limit to it, and we have to be careful about the point of inflection and number of concurrent flows in the network. And we talked about inner flow burstiness, and we suggested that this inner flow burstiness is causing drop synchronization in pace packets, which is causing throughput degradation. Another personal note, I actually believe that we don't really need to do per packet perfect pacing. I think that we actually would be able to get away with burst pacing instead of per packet pacing, meaning that we might be able to pace packets, but not every single packet individually. We might be able to get the same benefits of pacing with only doing a little bit of half of, say every 10 packets, let's pace every 10 packets instead of every single packet. But the research question here is that how little is little and how big is big, and what are the complexities versus the performance benefits that this might give us. And the last point for future work is the per-egress pacing, which I just introduced, and I think that it's going to help TCP pacing problems by introducing another level of pacing at the end host. And with that, I'd be happy to take questions.
Any question?
Yes, Mitch, IBM Research. Two questions. One, have you tried to introduce some jitter in pacing? Beyond the inflection point, you have shown that there are certain demerits. And is maybe introducing a small jitter going to alleviate or make no impact?
That's a great point. I actually believe that having some jitter in a network, my experiments were very controlled, and I wanted to just demonstrate this phenomena. So I didn't have any jitter in a network. But I do believe that having some jitter or randomness might actually help with this. But I don't think that the theory is going to go away. So there is going to be a point of inflection, but it might happen later.
All right. And the second question is about practical implementation. How could one figure out in a normal deployment what is the inflection point? You have a data center where there are probably millions of connections being active. When to turn on and off pacing?
That's a great question, and it actually leads to my PhD thesis that when we proposed the idea of having a controller in a network, say that we have a software-defined network, and the software-defined network has a view of what is the status of the network. Let's say that the SDN controller knows how many concurrent flows are happening, and this work was kind of a motivation for my thesis, saying that if we had some control over the network, that controller would have been able to, oh, let's enable pacing or let's disable pacing, depending on the status of the network. Thanks for asking.
Thank you.
More questions? Thank you, Monia.
Thank you.